Thank you, organizers. Thank you, organizers, for giving a chance to talk about my recent results here. My name is Kimitake Hayasaki. I'm purely Japanese, but now I'm affiliated with Chunbuku National University in South Korea. And they are my collaborators. Okay. So this is the outline of my talk. And first, I will very brief introduction about tidal disruption events. And then I will describe our numerical model and the detail about general relativistic treatment in smooth particle hydrodynamics code. And then I'm going to explain the three main results. And finally, I'm going to summarize my talk. Okay. So there are three main scientific motivations to study tidal disruption events. One is tidal disruption events are proof of supermassive black hole demography. And second, tidal disruption events are laboratory for super Eddington accretion and outflow physics. And also final tidal disruption events are one of gravitational wave source candidates. And this is the usual standard picture of tidal disruption event. And star approach to the black hole, and then tidal disrupted at the radius where the black hole tidal force just dominated the self-gravity force of the star. And the typical value of tidal disruption radius for 10 to the 6 solar mass black hole and 1 solar mass star is 100 solar radius, or 24 Schwarzschild radius. And after disruption, stellar debris, about half of stellar debris is away from the black hole because of positive energy by tidal disruption. And about half, remaining half, fall back to the black hole. And this is a typical time scale of a typical fallback time scale. And there are many numerical simulation studies of tidal disruption events in parabolic orbit. And the problem is how fallback mass finally accrete onto the black hole, because the angular momentum of stellar debris is conserved, so fallback mass is return to the tidal disruption radius. That's why we need the mechanism to circularize the stellar debris. So, but how fallback mass is circularized it still remains still a matter of debate. Okay. So this is there are two types of tidal disruption events depending on the original orbit of the star. And this is a summary of summary table of two type of tidal disruption events. So one is a parabolic standard TDEs, and here original stellar orbit is parabolic orbit, and binding specific energy is 0, and the peak value of mass fallback rate is 10 to the 2 to 3 Eddington rate. And as you know, where mass fallback rate curve is proportional to t to the minus 5 sub. And also the number of observed TD candidates or parabolic TD is about 20. And typical fallback time scale of most loosely bound orbit are estimated more than 300. And on the other hand, so in the case of eccentric exotic TDEs, the original stellar orbit is eccentric, and the peak value of mass fallback rate is 2 or 3 orders of magnitude larger than parabolic standard TD case. And mass fallback rate curve is spiked shape or delta function like shape. And the number of TD, observed TD candidates is 1. And typical fallback time scale of most loosely, most tightly bound orbit is much shorter than parabolic TDs. So the other aspect of eccentric TD is will be given by next speakers. I'm not sure. So look at this value. I mean, typical fallback time scale of most tightly bound orbit of 2 TDs. So because parabolic TD case, even even time scale, fallback time scale of most, even most loosely, most tightly bound orbit is more than 300 dynamical time. It means simulation time scale is very consuming, very time consuming, and that's why eccentric TDEs make it possible to perform simulations within realistic simulation time scale. So that's why our goal is to study effect of supermassive black hole spin on debris circularization, and this is a schematic picture of eccentric TDEs. And this is a spinning supermassive black hole here, and so this is a tidal disruption radius, and star is here, and the blue curve shows original stellar orbit, original eccentric orbit. And after disruption, stellar debris should be circularized like this. Okay. So this is the modeling of star black hole system by using SPH code developed by Benz and et al. And we use common parameter. So this is a black hole mass. Black hole mass is 10 to the 6 solar mass. And stellar mass is 1 solar mass. And this is the initial state of density map. And the star, so we put the star here, and the black hole is here, and then dashed circle shows the tidal disruption radius. And this is a extended star, and the initial direction of the star is here. And the star is modeled by a polytropic sphere. And we need to treat we need to be careful in treating treating the black hole particle or black hole potential because of general relativistic effect. So there are two types of basic equations. There are two basic equations in general relativity. One is Einstein equations. Here, this is this corresponds to the Poisson equation in Newtonian theory. And G mu nu is an Einstein tensor, and the T mu nu is an energy momentum tensor. And this is a geodesic equations. And this corresponds to the Newtonian equation of motion in Newtonian theory. And this is a acceleration term, and this is a host term. And tau is proper time, and gamma is Christoff's symbol, and this is a function of metric. So in normal usual procedure, Schwarzschild metric or Kerr metric are derived by solving Einstein field equations, and then substituting G's metric into the geodesic equations, we can finally get an equation of motion of a test particle. So similarly, in post-Newtonian approach, metric can be expressed by deviations from Minkowski flat spacetime metric because of weak gravitational field. And substituting expanded metric into the geodesic equations, we can finally test particle equation of motion with post-Newtonian corrections like that. And this is a Newtonian term and a 1pm term, and this is a spin induced acceleration term and 2pm term. So these post-Newtonian accelerations are incorporated into SPH equation of motion. So the problem is how do we treat hydrodynamic term in SPH equation of motion? So we can have order of magnitude estimate of each term in fluid equation of motion. And this is the example. So this is the order of magnitude of 1 pn gravitational acceleration, and this is a 1 pn pressure term, and this is a 1 pn self-gravitation term. So you can see so hydrodynamic and self-gravitative terms can be neglected because much smaller than the 1 pn gravitational acceleration term. So we can justify post-Newton acceleration involved in SPH application of motion. We can justify the only inclusion of gravitational acceleration into SPH code is enough to express general relativistic effect in tidal disruption event. Okay. And let's move to the results. So the effect of radiative cooling efficiency on this formation. So this is the typical value of optical depth, and so for electron scatterings, and the value is of the order of 10 to the 6, and this is the photon diffusion time scale, and this is a Holbach time scale. So you can see that the stellar depth is clearly optically thick for tidal disruption radius scale. So there are two types of radiative cooling efficiencies by comparison between Holbach time scale and diffusion time scale. And if Holbach time scale is longer than diffusion time scale, Davis orbital energy is converted to thermal energy by shock and radiate away quickly. And if Holbach time is shorter than the diffusion time scale, Davis orbital energy is converted to thermal energy by shock and stored into the debris. So because it is not so simple to treat radiative transfer in optically thick regions, we consider the two extreme cases, one in radiatively efficient cooling case and the other is radiatively inefficient cooling case. So this is an example of radiatively efficient cooling case. This is the original parameter of orbital parameter of original stellar orbit. And this is a penetrability factor, and this is a black hole spin parameter. The I is the inclination angle between the black hole spin and original orbital plane of original stellar orbit. And this is a density map animation of xy plane. Xy plane is the orbital plane, and the corresponding zy plane. And dashed line shows the tidal disruption radius. So you can see that formation of geometrically thin ring-like structure. Sorry? Small one, small white. This is a velocity vector. Velocity vector of matter. It's a particle, right? So pardon.
Is there fluid though? Is there fluid in the dark blue?
Yeah, it's free. And it's a velocity vector of fluid part.
But if the velocity is what? Is the matter distance? The velocity vectors in the outer regions are extremely undetermined, so there's not very much.
Oh, yes.
Why you have arrows there?
Because it's just from nature. The code velocity. Yeah.
Mm-hmm.
Okay.
Okay, so this is a radiatively inefficient cooling case. So the same simulation but for radiatively inefficient cooling case. So you can see the formation of geometrically thick disk. Okay. And the effect of black hole spin, especially upside precession in this formation. This is the test effect of upside precession test particle simulations. The starting point is here, and finish. Okay. Sorry. Okay. Sorry, summary. So post-Newtonian approach is an effective way to study supermassive black hole spin. Effect on debris circularization and radiative cooling efficiency effects on structure and evolution of debris circulation. Okay, that's all. Thank you. Excuse me? Black. Sorry, slow down, please. Yeah. So this is a non-spinning black hole case that fits particularly. This.
Yeah, if you go 2 slides forward.
Yeah.
Or 2 slides forward.
This one?
Further. Forward.
Oh yes, this is a.
Two more slides. If you go slides forward.
2 more.
1 more.
Oh, this is sorry.
One more.
One more.
Yeah, the next move is. Yes.
Okay.
So this is a rapidly spinning black hole and it's running in this line orbit.
Yeah.
This is efficient cooling.
Sorry, efficient cooling. And then the direction of spin is like that.
So here the strings remain thin enough to pass above and below each other, and circularization is clearly retarded significantly. But to answer Clement's question, in the inefficient cooling case, which is not this case, the strings pop up and out, but they just slam into each other, and the effective black hole spin does not slow circularization. Okay.
Do you have any idea how that compares to the calculation? Expected number of eccentric
Eccentric parabolic? That's good question. Maybe the right curve, the shape of right curve is more remarkable difference between parabolic TD case.
I'm asking about how is the observational case for eccentric versus parabolic compares to the
Observation rate?
But like, I'm asking like what would,
You,
I would say what's the theoretical
Variance. Probably eccentric rate.
Okay, we have to break for coffee. Until everybody wants coffee. We'll be back 3 minutes after 11 is the start of the next talk. Thank you very much.